pi is also there, right? Okay, I'll just twist it a little bit. This is E upon 2m into nh upon 2 pi, right? So magnetic moment is E upon 2m into the angular momentum. It is independent of z, which means it is same for all the elements, hydrogenic atoms, right? So you understand this, that actually the angular momentum would also be independent of z. It is mvr is equal to nh upon 2 pi for all the hydrogenic atoms, right? All the hydrogenic species we say, because it involves an atom and few ions, right? So for all the hydrogenic species, this L would be independent of Z, same for everyone, and similarly M would also be same for everyone. Okay, right? The minimum value for this would be, the minimum value for angular momentum is h upon 2 pi. So this would be E upon 2m into h upon 2 pi, right? This minimum value is called Bohr magneton. Bohr's magneton, right? You must have studied this when you were studying magnetic effects of current, right? Moving charges and magnetism chapter. I hope it's okay. Shall I erase it? Shall I erase it? Right? So now you understand what, from where Bohr magneton actually came, right? Now the last thing, which is energy. Okay. Now energy is of two types. Okay, the potential energy as well as the kinetic energy. So the potential energy would be how much? K Q1 Q2 by R. Okay, because of electrostatic forces, the energy is K Q1 Q2 by R. So this is K ZE into E by R, which would be K ZE. In fact, I should be writing ZE square by 4 pi epsilon naught R was how much? बताना होगा फिर से आपको. Epsilon naught. Okay, so if you write the potential energy, and it should be negative as well because the electron has a negative charge, right? So it would be minus, pi cancels, and this would be me4 by epsilon naught square h square into z square by n square. Right? The kinetic energy would be K is half mv square. So this is half m. V is how much?
E square by 2 epsilon naught h into z by a
This was
whole square.
V, this was V. So we replace the values, we get K as, so this would be ME4 by 8. I left 4 here. Please check, I forgot 4 here. It was 4 as well there. Okay. So this would be 8 epsilon naught h square into z square by n square. The kinetic energy is minus u by 2, right? Okay, the potential energy is this expression, the kinetic energy is minus u by 2. Okay, and you can say this is minus 2k. Kinetic energy has to be positive always, potential energy is negative always, right? Attraction is there. Shall I erase this? Huh? Nahin? Hmm? Shall I erase this? Okay. Now, so the total energy would be potential energy plus kinetic energy, which is u plus k, and this is, how much was the value? Minus m
e to the power 4 by 4 epsilon naught h square into z square by a epsilon naught only z square by a
epsilon naught square tha, z square by n square, right? Plus the kinetic energy of was half of it, but positive z square by n square, right? So the total energy E is minus me4 by 8 epsilon naught square h square z square by n square. Now if you put the values of all the constants, this becomes minus 13.6 z square by n square EV. Okay, we have put values of h in electron volts. H is what? Planck's constant. Okay, it is converted into electron volts. Karen, shall we? Shall I erase this? So before we move any further, let's do one or two questions. Now the question was, the energy of an electron in an orbit of He plus is minus 13.6 eV. Is it okay? Is minus 13.6 eV. Find the angular momentum of electron in this orbit.
Chapter 5.
I hope people online are also solving this. This was a very easy question. The energy is how much? Minus 13.6 z square by n square, which is given as minus 13.6. So this, you can see z square is equal to n square. Z for helium is 2. So basically n has to be 2. For second state, or second orbit, the angular momentum is 2h upon 2 pi. No need to calculate MVR. Okay, this is while we are studying the Bohr model, so you are applying this. Okay, if I had asked this question, let's say some weeks later, you would have actually started doing it using MVR. Everybody forgets that you need not use MVR anytime in the Bohr model. You can always apply NH upon 2 pi, right? Okay, shall I erase it? Okay, several objective questions had been asked, not in JE, very early in AIEEE, when it was not JE actually. In AIEEE, several objective questions were asked on this idea, that the dependence basically. So it was like that if in second orbit of hydrogen, the electron speed is V naught, what is the electron speed in third orbit of lithium, let's say, right? Is the electron speed for n equal to 2 in H, it is the speed is V. So the question asks, find velocity in third orbit of lithium. Okay, so you can apply it directly if you know the logic, if you know the dependence, right? The dependency, right? So you can do it, or maybe we can move on. Your idea, your wish. Okay, several questions of this type were asked. So they may come in easier exams. I don't expect them to come in JE directly, but they may form a part of a bigger question actually. Our question may be asked for some other thing, and it uses this kind of thing. So instead of actually solving it, if you know the dependence, we can use it. For this question, you can understand V was how much? It was, yeah, it was proportional to Z by N, right? So in ground state, this was given. This was, so in ground state, the velocity would be double. It is inversely, Z is 1, right, for a hydrogen. So velocity is inversely proportional to N. Okay, so in ground state, the velocity would be 2v naught. Okay, for some other scenario, so V3 for lithium, Z is 3. So this is 3. It is the ratio is still 1. So the velocity would be again 2v naught. The ratio is 1. Velocity would be 2v naught. Okay, I'll erase this. This was easy one. Please, check out the questions of this type. They are easy, direct questions. If you solve them today itself, you would be able to solve a lot many questions without any hassles. But if you take a few days break or waiting time, then you would have to go through all the concepts first. Then only you can do the questions. We forget these dependencies, right? So now let's discuss the electron transition. Is it okay? The electron transition. Okay, the electron transition. So let's check out. Let's say this is N2, few others are also there. This is N1. The electron transits from N2 to N1. Some energy is released, a photon is released. So we already know that H nu is equal to E N2 minus E N1, right? Okay, and Hc by lambda is, what's the expression for energy? Please, if you could just again guide me. Minus Me4 right, something like this. This is common, So I'll just write n2 square minus 1 by n1 square. So 1 by lambda is minus m e4 by 8 epsilon naught square h cube c. I'll take negative inside. This is z square 1 by n1 square minus 1 by n2 square. This whole thing is again a constant. This whole thing is a constant. It is called Rydberg's constant. So this whole thing is called Rydberg's constant, right? The wavelength of the photon emitted would be this, and the condition is that n2 should be greater than n1, right? This has to be a positive value. So always place the smaller orbit number in the front. Right? Okay. Shall I erase this? One more thing, let's just write the values for different. Let's just write the values for different nuclei. This is n1. The value for this, the energy for this would be minus 13.6 z square. For n2 minus 3.4 z square. You remember the formula is minus 13.6 z square by n square. I'm just putting the values of n. It becomes handy if you remember them. This is minus 1.51 z square. n4 is minus z square, and n5 minus 25 0.54 z square, right? Rest we need not remember. You can apply on the spot, right? One more thing, I'll erase that headline, add something else. Now if the order is infinity, if the orbit number is infinity, the energy is 0, right? The energy is 0. Okay, so you can see so many transitions are possible. Okay, so many possible energies of photons, but not all, right? One more thing, a few definitions. Ionization energy, somebody has asked something, why the difference between is more in energy. Why this? You can see the energy is this. As values of n increase, okay, as values of n increase, so basically the value, the decrease in energy becomes smaller and smaller. The decrease in energy becomes smaller and smaller, right? You can see, just put the values. Just put the values here, okay, and you can check the values become, even they change very little later on. Start in at first they change very rapidly, then very small change is there. So the thing we would study is ionization energy. It is energy required to remove an electron from ground state, which is n is equal to 1 to n tends to infinity, right, to the outermost possible state. So in that case, how much is the change from here to here? You need this much energy, okay. So the energy needed, the IE is actually plus 13.6 Z square, right, plus 13.6 Z square. And this is also called binding energy. Why it is called binding energy? Because this is the energy which is actually released when an atom is formed, okay. So because of this release of energy, the electron is bound to atom, okay. If we express, it is mostly expressed in the form of electron volts. If we express in the form of volts, it is called ionization potential, okay. It's the same thing in volts. So the ionization potential IP is actually nothing but plus 13.6 Z square volt. Somebody said, please explain questions based on V, Z and N. We would discuss, just wait. Kare, shall we start? Sir, does it mean the binding energy per electron is IP? Actually, there is only one electron, so I would not use the word per electron because it's just one electron. Is it okay? All this was derived for only one electron in the species, right? So I would not use the term binding energy per electron. It's just binding energy, okay. And actually we use the term potential just to express it in the form of volts. You remember this, that if between two plates, if V is the potential difference, this is positive, this is negative, I release an electron from here. By the time it reaches the positive plate, its kinetic energy becomes EV, right? EV. So I can omit the word E from the energy, okay, and get things in volts. I was using the same logic. So ionization potential is actually by definition it is the potential through which an electron should be accelerated so as to have same energy as that released as that required for ionization, So it is the potential through which the electron, I'll write IP, the definition, the PD, potential difference through which an electron should be accelerated so as to have energy equal to ionization energy of the atom. Not the atom, basically the species, because we don't know whether it's an atom or an ion. Is it okay? Shall I erase this? Somebody said, is the IE and IP independent of N? What do you think? The ionization energy is this. Okay? The ionization energy is this. Actually, N is 1. It is this. Okay? Ionization energy is the energy required to remove an electron from the ground state, from 1, N equal to 1. So it has to be independent of 1. It involves removing electron from orbit 1. It's independent of N. Okay? Not, we don't define ionization energy for this state, that let's say electron has been removed from third. It's not called ionization energy. Okay? It can be asked in a question, but the question won't use the word ionization energy for this. Right? Shall I erase this? Now, again, electronic transition. Okay, electronic transitions. Let's check these out, the transitions. So from this was 5, I'll draw one more 6 orbit as well. So whenever electron jumps and reaches n equal to 1, okay, whatever may be the starting orbit number, starting order, it always ends at ground state. Okay, these are called what? The Lyman series lines. Why? Because if the electron, if this kind of transition happens, the photon which is ejected comes in the UV region. Okay, comes in the UV region. So this is Lyman series. Then if everything ends at 2, this is Palmer series. If everything ends at 3, this is Paschen series. Okay, I'll erase this. Okay. For this transition we call it bracket, and for this transition it is P fund. So this is UV, this is Balmer is visible. All the transitions in Balmer series produce visible photons, while all these produce infrared photons, right? Okay. For every possible transition, there would be a unique photon. Okay. If the light emitted through it, if the light emitted through this arrangement is passed through a prism, what we get? We get a, if the light emitted is passed through a prism, what we get on the other side? The wavelengths are arranged in an order of, increasing wave. The lights, basically, the photons are arranged in an order of increasing wavelength. So here this is minimum wavelength, here this is maximum, and one transition, one photon, one type of light would be represented like this. So there would be a few lines like this. Some would represent Lyman, some would represent Balmer, and so on, right? So this is called the line spectrum, the emission line spectrum, right? This is called the emission line spectrum. Right? You know what is absorption spectrum? Absorption क्या होता है? When sunlight is incident on, let's say, this gas, whatever it was, so from all the wavelengths, few wavelengths are absorbed by the gas, right? Okay. And if we allow the light which has passed through the prism, if we allow the light which has passed through the prism, what happens? If we allow the light, let's say sunlight is passed through this gas sample, and then it is passed through the prism, we would see a continuous pattern from red to violet. Okay, we would see a continuous pattern from red to violet, out of which few lines from here and there would be missing. Some fine areas, some narrow areas would be dark. This is called absorption spectrum, which means actually some lines were absorbed from all this arrangement. Some lines were absorbed from all this arrangement. Is it okay? The other thing is absorption line spectrum, right? The other thing is absorption line spectrum, right? Shall I erase this? Now, last but not the least, the number of transitions. Or number of lines, basically, because as many transitions possible, and as many would be the lines, right? For every transition there would be one line. So let's try to understand. Here from let's say I'll show 4 orbits. Okay, let's try to understand how many possible transitions would be there from 4 to 1. Is it okay? We would find a formula, but based on our experience here. So this is one transition possible. From here, array can electron can transit from here to here, from here to here. Okay. Okay. Since a gas has so many samples, these 3 transitions from the 4th orbit would be possible, right? For some atoms or maybe some ions, electron would directly jump from 4 to 1. For some it would jump from 4 to 2, then 4 to 3, then from 3 to 1 a transition, and 3 to 2 may be possible. Then from 2 to 1 it is possible. This is 6. The number of transitions is 6, right? Okay. And you know, the transition, you can, this would be a combination of basically the number of ways of selecting 2 possible things out of a group. I would write this as, can I write this as 4C2? By experience, we would write this as 4C2, right? So this is 4C2, right? If there was 5th as well, then from 5th some other transitions would have been possible. Right? 4 more transitions, then the total transitions would have been 10, then 5C2. Is it okay? But what if the transition does not end till 1? What if the number of the transition does not end till 1? So all these transitions would not be there. I'll directly write the formula now based on the understanding. It is nothing but N2 minus N1 plus 1 C2. Just check this out. If N2 is 5, N1 is 2. From 5th to 2nd, the transition has happened. From 5th to 2 to 2nd, the transition is happening. Okay. Just think about it. Number of lines would be 6. You can understand this. 5 minus 2 plus 1. 4 C2, right? All correct. So the number of transitions, capital N, can always be written like this. Since most of the time N1 is 1, so it would be NC2 directly, right? Okay? If N1 is 1, capital N would be N2C2 directly, right? Okay? And N2C2 would be actually nothing but N2 into N2 minus 1 upon 2. This is N2C2, NC2 is this, N into N minus 1 by 2. So this is indicated in NCERT and a lot other texts. But what if the ending line is not, the ending orbit is not 1? So in general case, this is the formula. In specific, you can go like this. Shall I raise this? Shall I raise this? Right? I guess all is done. Only one thing is remaining, which is de Broglie's explanation of the second postulate, or rather proof of second postulate using de Broglie hypothesis. Only one thing is remaining, which is a part of CBSE. I would discuss this slightly later. Just first finish a few questions. Somebody asked, what is, somebody asked the question. What was the question? Yeah, somebody asked questions based on relation between V, Z and N. It, it may be R, Z or N. It may be energy, Z or N. Okay. Questions may be based on all this arrangement. So a question on this. The radius of ground orbit of hydrogen atom is A naught. The radius of n equal to 2 orbit of Be3 positive atom is, this is easy, right? If you know the expression, it won't be a difficult task to handle it. A naught by 4. See, for beryllium, Z is 4 and N is 2. It's given. R is how much? A naught into how much? Z square, N square by Z. Sorry. This is N square by Z. 4 कैसे आ रहा है? So this is actually 4 upon 4. It is A naught only. Okay. Okay. Similar kind of questions can be there. The velocity of electron in second orbit of hydrogen is something. Then find the velocity in this orbit. Something like that. Right? Yes. The answer is correct. Somebody from online answered it. Shall I erase this? These are easy questions. Let's start with better ones. Okay. Okay. There are, in the JEE exams, the questions had been asked on transitions, and also the questions had asked you to derive model based on some hypothetical conditions, that a hypothetical atom has potential energy of this form. So now solve, right? So we would discuss all that. Now the first question is this: let AN be area enclosed by nth orbit of hydrogen. Atom. Okay. So plot ln AN by A1 versus ln N. Okay. You know the radius, find the area, plot. I'll give you some options. Let's see. right? Which one? Let's check. What is the area? Area of orbit is pi r square. Now tell me the expression. You need to tell it again. How much is the what is the expression for radius? Epsilon naught n square by h square by pi m square, and it is square of this thing. What? N square by z. Okay. Sorry. समझ आ गया. So square of this thing. So it would be pi epsilon naught square h4 by pi square m square e4 into n square by z square. Since z is 1, I will remove z, right? Z is 1, it's hydrogen, है ना? This is area of nth orbit. If I divide it by a1, all of these constants would go. A n by a1 would be actually n square. If I take ln of this, किसकी? अच्छा, 4. If I take ln of this, it would be 4 ln n. So the graph of this versus this would be a straight line, y is equal to 4x form, straight line passing through origin. So the plot would be a straight line, but actually this is not the correct answer. Why? Because not all the possible values of n can be there. Not all the values of n can be possible. Only integral values of n are possible. So a point would be there at n equal to 1, a point would be there at n equal to 2, and so on. So the slope of this hypothetical line would be 4. The points would lie on a hypothetical line of slope 4, but there won't be any line actually, right? Shall I raise this? So the next one, I hope this was clear, right? Again, it was a question of, relation between area n and z, right? Okay. So the questions may range from one thing or to other. You asked, somebody from online asked the question based on v, n and z. So I gave you much more. I gave you area. Okay. Same thing can be asked for magnetic moment, for magnetic field, whatever. Okay. So now the next question, you need to find the minimum and maximum wavelengths for Lyman series. Okay, minimum wavelength and maximum wavelength emitted for Lyman series. Lyman series of hydrogen, इसको लिख लो. Z should be given actually. That is 1. Lambda max is 1 by R. Value निकालो. You need to find the values in nanometer, angstrom, जो भी. चलो, I'll tell you how to use shortcuts. I told you HC is actually 12400. बताया था last time. Okay, it's written everywhere. You can use it directly. Please don't use मेहनत वाला सब कुछ काम, right? Actually, that Rydberg formula can be used, and another way is to find the amount of energy as well, right? So this is minus 13.6 for minimum wavelength. Minimum wavelength means highest possible energy. Highest energy happens for n is equal to n tends to infinity to 1 transition. Okay, right? Getting the idea? Somebody asked. Okay, some answer is there. Let's discuss. So the minimum, highest energy state. A photon of maximum energy is emitted when the transition is from infinity to the ground level. The energy involved is how much? 13.6. From 0 to 13.6 आ जाता है ना. Energy here is 0, here it is minus 13.6. So the energy of photon would be 13.6. E is hc by lambda. So lambda would be hc, which is 12400 by 13.6. You can find lambda from here. One way was this. Another way was using Rydberg's constant. 1 by n1 is actually 1 and n2 is infinity, right? So one way is this, 1 by r. These are two independent methods. You should know both of them. I won't be telling you the answers. I cannot calculate, right? You should calculate these. So they would be somewhere around what? कहाँ होगा? This is 91.1 nanometer, or actually it would be in angstrom, 911 angstrom Why? Because the numerator is EV angstrom and the denominator is in EV, so only angstrom units are remaining. So this is 911 angstrom. Okay, from this one as well you would find it as 911 angstrom. For minimum, this was minimum, lambda minimum. Lambda maximum would be how much? Again, minimum energy photon would be released for n equal to 2 to 1. There is the transition which involves least energy and maximum wavelength, right? So this is minus 3.4. Okay, so this is 10.2. The transition energy is 10.2. Photon would carry 10.2. This is 10. This is 12400 by 10.2. Okay, angstrom. This would be 1211, somewhere around 1210 angstrom. Okay, since both of them have less wavelength as compared to violet, which is 3000 angstrom, they would be in ultraviolet region, right? So this was an easy one. Let's discuss a better question. Okay, shall I raise? An atom is excited to an energy state in which for which emission spectrum has 6 lines. For which emission spectrum has 6 lines. Okay. Why? Okay. The emitted photons are एटम का Z ले लो आप 3 एक्चुअली ओके 2 ले लो आसानी रहेगी एटम का Z है 2 राइट an atom Z equal to 2 is excited to an energy state for which emission spectrum has 6 lines while the atom comes back to ground state. The emitted photons are incident on a photoelectric metal of work function 2.1 electron volt. ठीक है, find the stopping potential of ejected electrons. Right? So now you understand I have mixed the two concepts. This happens very frequently in the actual exam. Stopping potential. Huh?
minus 6.5.
-6.5. Okay, let's start. Now let's check. Z is 2, right? Okay, Z is 2. So, and there are 6 lines. Emission spectrum has 6 lines. 6 lines, and the final state is ground state. It can happen only when the initial state is 4C2, right? Okay, 4C2. So, the excited state is n equal to 4, and from there the electrons come down, right? Now, let's draw the energy levels. For ground it is minus 13.6 into Z square. Okay, so minus 13.6 into 4. How much would it be? कितना होगा? बता दो. This would be minus 3.4 into 4, minus 1.51 into 4. This is minus 0.85 into 4. Right? यही होगा ना? Now the possible transitions are these. These 6. Okay. Out of these, which transition do you think emits the photon of maximum energy? किस ट्रांजिशन में मैक्सिमम एनर्जी फोटोन रिलीज होगा? आउट ऑफ ऑल दीज ट्रांजिशन, which transition releases photon of maximum energy? किस वाले में? In this one? In this one? The maximum energy photon is released in this case, so the energy of photon would be how much? Difference of these two levels, right? How much कितना होगा? How much? कितना होगा? 12.75 into 4, ऐसा ही कुछ हो रहा है? 12.75 into 4, 51. This would be 51 electron volt. Okay, 51 electron volt. The photons of energy 51 electron volt or lesser, because there are 5 more type of photons, are incident on metal of work function 2.1. Is it okay? Are incident on metal of work function 2.1. So the maximum kinetic energy of electrons would be how much? 51 minus 2.1. This is 48.9 electron volt. To stop these electrons, you need stopping potential of 48.9 volts. So this is the answer. Okay, the logic which I applied, there can be 6 type of photons, but only this photon would give me an electron of maximum energy. Only this photon, this highest energy photon, would eject electron with maximum kinetic energy in photoelectric effect, right? It has highest energy, it would give me an electron of highest kinetic energy. So if I stop that highest kinetic energy electron, I would be able to stop all others, slower electrons as well. So I try to stop the highest kinetic energy electron, and that's why the stopping potential for highest kinetic energy electron is this, right? So I hope I can erase this. है ना? Two concepts really mixed well. Now a different variety now. Shall I erase this? No. At least I can erase the question. first. So in a hypothetical atom, the potential energy of electron is given by U is equal to AR square. Right? Shocked? Huh? U is equal to AR square. Find expression, hypothetical H atom ले लो, take Z as 1. Okay? Makes things easier. Find expression for L, which is the angular momentum, okay, and V as well. Okay, we can find expressions for kinetic energy, potential energy, and all other things as well for this, but I am interested only in finding just two quantities. So how to solve this kind of question? See, the potential energy is AR square, and you know the conservative force acting can be written as minus du by dr. ये पता है या नहीं पता है? You know this or not? You studied this when you were studying work energy power, right? Okay, that potential energy is negative of work done due to conservative force, right? Or we can say conservative force is negative derivative of the potential energy, right? So this would be minus 2AR. Negative sign indicates the force is attractive, right? The force is attractive. So this attractive force provides the centripetal force. So mv square by r is equal to 2AR. I'm dropping the negative sign because we know it is attractive. Okay, so only the expression we are using. mv square is equal to 2AR square. Another form, another postulate is, this is using the first one. The second postulate is mvr is equal to nh upon 2 pi. Use this one as well. Okay, you can write r as mv square by 2a under root. So this would be mv into mv square by 2a under root is equal to nh upon 2 pi. Okay, right? The expression for angular momentum basically remains same, right? So this would be m square v raised to power 3 by 2, sorry, m raised to power 3 by 2 while v square upon root 2a is nh upon 2 pi. So v would be how much? nh root 2a by 2 pi m raised to power 3 by 2 and whole of this power half. Velocity would be this. Okay, the angular momentum would be again nh upon 2 pi. Okay, because you know if this condition is not valid, Bohr model would no longer be valid. So if you are using Bohr's model for this hypothetical atom, even then this condition would be valid. Okay, you can find, since you know V now, you can find R, okay, and you can find all other values, possible values. Questions had been asked in JEE on this time and again, right? Okay, shall I erase this? Now, proof of second postulate using de Broglie's hypothesis. Okay, second postulate said that mvr is equal to nh upon 2 pi, है ना? Now, what de Broglie said, that matter exists as particle and wave, right? So moving electron in the orbit must exist like a wave. So moving electron exists like a wave as well with wavelength h upon p, or which is h upon mv, right? Okay, now you can understand wave particle is a point entity, while wave is a spread out thing. Wave spreads everywhere. So if electron is existing like a wave in this orbit, okay, different parts of the wave would interfere with each other. Let's say from here it exists like a wave. So on both the sides this kind of arrangement would be seen. Okay, different parts of the same wave would interfere, okay, and they would produce what? Standing waves, right? They would produce standing waves. So different parts of wave would interfere, producing standing waves, right? Now only those orbits are allowed in which standing wave just a second. Slide गड़बड़. Okay, only those waves are allowed in which standing wave, is complete, like this, right? Right? Standing wave is complete. So only those orbits are allowed in which integral multiples of wavelength exist. So for which you can say only those orbits are allowed in which circumference is integral multiple of wavelength. So this is 2 pi r is equal to n lambda, or 2 pi r is equal to h upon mv, and from here you can see mvr is equal to h upon 2 pi. So from here we understand how he actually got the idea of nh upon 2 pi, angular momentum nh upon 2 pi. Shall I erase? Shall I erase? One last variety which was asked in JEE, which is atomic collisions. What is atomic collision? Just try to understand. Let's say one hydrogen atom is moving towards another hydrogen atom and they collide. Okay? Okay, one hydrogen atom is moving towards other and they collide. Two possibilities are there. In fact, three. One possibility is that the collision is elastic. Okay, the energy is transferred or whatever. You know the concept of elastic collision. You know the formulas. So the redistribution of energy happens in elastic collision, and there is no loss of energy. Second event also may happen, that if the energy of the hydrogen atom, first hydrogen atom is sufficient enough to cause an excitation of electron. This may be possible, right? Understanding this, that if the energy of hydrogen atom is sufficient enough, it may cause excitation of electron in the other atom. Okay, so due to this, some kinetic energy is lost. The collision is now inelastic. Okay, the extreme case of this scenario would be if the two atoms, they move together, which means there is no separation now. Okay, in that case collision is completely inelastic. Okay, and the energy is maximum amount of kinetic energy is lost, not totally, but maximum amount of kinetic energy is lost. Please note, in all three cases linear momentum would be conserved. So this thing would never happen, that an atom is kept here, another one comes, hits this, and they both stop. This would never happen, because this violates conservation of linear momentum. Is it okay? This violates conservation of linear momentum. So total loss of kinetic energy is never possible, because then it would violate conservation of linear momentum. In one case, total loss of kinetic energy is possible if they are moving with equal momentum in opposite direction. There is a head-on collision like this. They move, okay, they move toward each other and collide. The momentum initially was 0, finally is 0. So a total loss of kinetic energy can happen in this scenario. So I'll I'll jot down the important aspects of this scenario. Let's say this is the kinetic energy. This is one atom. Okay, they may have same mass, they may not have same mass, and a possibility might be there that this projectile body, the body which is projected, may not be an atom. It may be a nucleus. Okay, a neutron, a proton, some other particle, right? Is it okay? Okay, in any case this logic everywhere applies. So this is atom, H type atom. Okay, okay, so three possibilities. One is elastic, other is inelastic. Obviously elastic is the easiest to handle in this case, right? No excitation ka drama, right? Inelastic, what would happen? And third case is perfectly inelastic, but I would write it later on, because it's just a special case of elastic. So in this case, let's say this one has mass m1, velocity v, this one has mass m2. Let's say the kinetic energy of first one is k, because most of the time the kinetic energy is given in electron volts, not the speed, right? So the momentum m1v can be written as under root 2 m1k. You remember this? So by conservation of linear momentum, it would be m1 v1 plus 0, m1 v is plus 0 is equal to m1 v1 plus m2 v2, right? This would be root 2 mk, m1k is equal to root 2 m1k1 plus root 2 m2 k2, right? K1 and K2 are their kinetic energies, right? Okay. What happens that actually kinetic energy provides K1 and K2, and it also causes excitation energy. Okay, so while this condition should always be true, this may or may not be true. You know, if the kinetic energy is not sufficient to cause an excitation, there would be elastic collision for sure. Okay. Okay. Now this, in case of perfectly inelastic, V1 and V2 are same, right? So for perfectly inelastic, m1v is equal to m1v dash plus m2v dash, or this would be again, no, it won't affect a lot, 2m1k1 plus root 2m2k2. Shall we start? Hmm? Shall we start? We need to do one question very quickly before the class ends. Now let's check out. Let's check out. The question says a neutron has mass same as that of hydrogen atom, almost same, right? A neutron moving with kinetic energy K collides with a H atom at rest. ठीक है? For which of the following values of K, collision would be elastic, inelastic, and perfectly inelastic. First value is 14 electron volt. Second one is 20.4 electron volt. Third one is 22 electron volt. That's it. Okay. Now how to solve this kind of question? Just think about it. this is nothing but a case of, you know, the neutron has mass m, kinetic energy k, the hydrogen atom has mass m as well. Okay, right? So let's try to find the minimum and maximum energy loss possible. Okay, right? You know, minimum energy loss would be how much? Is 0 for elastic. Okay, for maximum energy loss, what happens? Energy loss is maximum in case of what? In elastic collision, right? Remember this, energy loss is maximum in case of perfectly inelastic collision. Please be very specific about it. Okay, so maximum energy is lost for perfectly inelastic collision. Okay, when perfectly inelastic collision is there, what happens? Both of them move together, right? Let's say v is its speed, k is energy, right? K is kinetic energy. V is not given, we just use it. It makes us handling things easier. It makes things handling easier. So both of them would move with velocity v dash, same velocity. So by conservation of linear momentum, you can check that initially momentum was this, finally momentum is 2m into v dash. Both of them are moving with same velocity. So v dash is v by 2. Okay. Initial kinetic energy was half mv square. Final is, you know, sum of kinetic energies of these two bodies. So loss of kinetic energy would be k1 minus k2. Initial is half mv square. Final is half mv dash square. V dash is v by 2 whole square, twice of this, because there are two masses, moving with v dash speed. So if you find it, it would be half mv square minus 1 by 4 mv square, which is actually 1 by 4 mv square, or which is k by 2. Okay, so just try to concentrate now that the maximum kinetic energy lost can be k by 2. Okay, so now the kinetic energy lost would be in this order. Okay, this one is this much information we need in every case. Whether if the masses are different, you need to calculate loss of energy. Now with the loss of energy, we would try to understand whether it can excite an electron or not. So in first case, this loss of energy is how much? The kinetic energy was 14, so the loss of energy is delta k is from 0 to 7. The minimum energy, I'll draw the diagram. The minimum, this is minus 13.6, this is minus 3.4, this is minus 1.51. Minimum energy needed for one excitation is how much? 10.2. Okay, since this energy loss is less than 10.2, collision would be elastic in this case. For second one, the kinetic energy was 20.2, so 10.2. The kinetic energy was 20.4, sorry. So the energy loss would be this much. So actually, in case of perfectly inelastic collision, this might be able to just excite the electron to second state. So the collision here would be perfectly inelastic. What about the third case? There it is 12. So the energy is, maximum energy lost can be 11. Out of that 11, 10.2 can cause excitation and some energy would still be remaining. So the energy loss would not be 11, actually it would be only 10.2, while rest of the energy would be, you know, divided into two masses. Is it okay? So the collision in that case would be elastic. Oh sorry, inelastic, not perfectly inelastic, inelastic. Okay, right? So with this we end atomic structure. Okay, thank you all.